Hello, warriors. This is Miss Lemons, and now we are going to be going through question number 7 and 8 from your standard heats of formation practice. All right, so number 7 says calculate the heat of the reaction delta H naught for the decomposition of calcium carbonate, or CaCO3. So we've already been provided the chemical equation for the decomposition of CaCO3, and it's already been balanced for us. So this is the formula that we are going to be using. So we need the sum of the heats of formation of the products minus the sum of all the heats of formation of the reactants. And remember, heat of formation is the amount of heat required to create whatever substance we're looking at from its component atoms. So what is the amount of energy required to create calcium oxide using only calcium and oxygen atoms? Okay, so you will be provided the standard heats of formation for each of the compounds that are in the chemical equation. I went ahead and I showed you guys what the standard heats of formation are actually showing us. They won't be written like this on your test, but or on any other worksheet, but I just wanted to remind you that these values, standard heats of formation, are derived from the combination of atoms to create the substance that is in the chemical equation provided to you. But really, they'll be provided to you so they look a little bit more like this. So the standard heat of formation for CO2 is negative 393.5 kilojoules per mole. The standard heat of formation for calcium oxide is negative 635.0 kilojoules per mole, and the standard heat of formation for calcium carbonate is negative 1,207.0 kilojoules per mole. So we can go ahead and plug this information into an equation, kind of set this up for us. So the first thing that I want to do is pay attention to the products. So we've got only 1 mole of calcium oxide, which has a standard heat of formation of negative 635.0 kilojoules per mole. We're going to add that to only 1 mole of CO2, which has a standard heat of formation of negative 393.5 kilojoules per mole. And again, I just got these from over here. They were given to me, and they always will be given to you. So I went ahead and added those two together, and I ended up with a total of negative 1,028.5 kilojoules per mole for my products. Now I'm going to calculate the delta H, or the standard heat of formation for my reactants. I only have one reactant, and I only have 1 mole of reactant, so I have negative 1,207.0 kilojoules per mole for calcium carbonate. Okay, now that I have the standard heat of formation of my products and the standard heat of formation of my reactants, I can plug these values into my initial equation to get the standard heat of the reaction. So the standard heat of the reaction equals negative 1,028.5 minus negative 1,207.0, which gives me 178.5 kilojoules per mole. And this delta H also tells me the direction of heat flow. So if you end up with a positive number, that means we are gaining energy. Therefore, this is an endothermic reaction, or heat is entering the system. So this equation, or this reaction, happens to be endothermic. Okay, so let's take a look at question 8. We've got calculate the heat of the reaction, or the standard heat of the reaction, delta H naught, for the combustion of CH4. So that is CH4 plus 2 moles of O2 yields CO2 and 2 moles of H2O. So here are all the standard heats of formation that you will be provided. And again, just wanted to point out that each of these standard heats of formation come from taking the component atoms and pushing them together to create that substance. So we have been provided all of the standard heats of formation, but you'll notice that we actually have 4 substances up here, not just 3. But you were only given 3 standard heats of formation. So how are we supposed to figure out the standard heat of formation for O2? Well, single atoms, so if this was just O by itself, which would never happen, or diatomics, which are molecules that have to bind to themselves, that's Han and the halogens. Remember that memory trick from the beginning of the year. So single atoms and diatomics, they actually have a standard heat of formation of 0 kilojoules per mole. So this counts as 0 kilojoules per mole. So again, your standard heats of formation will actually be provided more like this without the equation, just so you know that this is the standard heat of formation for CO2. The pink one is the standard heat of formation for CH4, and the bottom one is the standard heat of formation for gaseous H2O. Now, I do point out gaseous because it's important. You see, the standard heat of formation for gaseous H2O is different than the standard heat of formation for liquid H2O. So please pay attention to your states of matter. Okay, so we're going to go ahead and calculate the standard heat of formation for the products. We only have 1 mole of CH4, so we don't have to multiply this by anything. And we only have 1 mole of CO2, so we don't multiply by anything. We have 2 moles of gaseous H2O, so we would multiply this value by 2, and then we'd add those two together to get us a total of negative 877.1 kilojoules per mole. We're going to do the same with the reactants. I only have 1 mole of CH4, so I don't need to multiply this by anything. And then I'm just going to show you guys the math for this. The standard heat of formation for gaseous oxygen or diatomic oxygen is 0, and there are 2 moles of it, so you would multiply that by 2, which would just end up getting you 0. So our total for the standard heats of formation for the reactants is negative 74.9 kilojoules per mole. So now that I've calculated my standard heats of formation for the products and the reactants, I can plug these values into the original equation and solve for the standard heat of the reaction. So I've got negative 877.1 minus negative 74.9 gives me a total of negative 802.2 kilojoules per mole. And remember, we can always use this final value to help us figure out the flow or the direction of heat energy. And in this case, this is a negative delta H value, which means that heat is leaving or exiting the system, making this reaction exothermic reaction. If you guys have any other questions, please reach out to me via reminder email. You can also do video chat with me. But hopefully walking through these 2 practice problems have given you enough clarity to figure this stuff out on your own. Thanks, guys, and good luck.